Well, thank you everybody for attending this evening. John has just told me that there's 100 people online, and we've probably got 30 odd people in the room. So thank you very much indeed for coming to attend Michael's talk. John, before we start, John's just going to take you notes about the upcoming meetings, and there's one other little thing he wants to talk about. Okay, Jim.
I've forgotten decryption. Okay. In February, we have the joint meeting with the SMEA and the South Yorkshire Industrial History Society. That's March. Sorry, it's all not really. That's at the Royal Victoria. It starts earlier. It's 5:30, and it's the talk is on the beauty of sin. The next talk after that is in April, 22nd of April, when Phil Judkins will be speaking on, and you think that it can fly. This is looking at the experimental work done at Sherborne Airfield at the start of the Second World War, and we have pictures of flying units. So something very different. And the final talk of the year is David and his colleague John Tanning, who are going to speak about the Barkers of Rotherham, who were some of the earliest adopters of the Bessemer converter and the Stephenson converter.
Yeah, they actually bought Bessemer, the company of Bessemer in Sheffield. Before that, it was John Baker and Sons Limited. Then they bought the Bessemer company in Sheffield, so it became John Baker and Bessemer. They made railway axles, railway wheels, railway tyres, and during the war they made shells, First World War and Second World War. So John's going to talk about the family history because John Anning is part of the Baker family. And I'm going to talk about the steel making and the processes. It was a very, very innovative company. And all the equipment, as far as I know, in the plant was designed and manufactured within the company by the Baker family. So I'm just putting together the slides now for that talk. John will be pleased to know.
During the summer, we're going to try something different. It would be very helpful to get some feedback on this. Prior to COVID, we managed to organise a number of visits to various locations. And the proposal is that we try to get those going again this summer. We've identified two venues to visit. One is the Rolls-Royce Heritage Collection. We're limited to 15 people there, and this is in Derby. We'll worry about travel arrangements, etc. If people either in the audience or online are interested in joining us on that, if you could let me know the email, use the email.
Your voice is very bad.
That mean they can't hear you, John?
Okay, we'll have a look at the sound issues, but it should be okay.
It is now.
Not everybody's reporting problems. Okay. The second one is the possibility of visiting the Doncaster.
Still can't hear you.
We'll ask the person in the audience, we've got somebody in the audience of this. Can you hear the sound?
Got a bit close.
Okay. Well, okay. Okay. So the people on slide can't hear. Could you please turn your volume up? Others are saying it's okay. The second visit is to the Doncaster Aircraft Museum. This is more relaxed. We can take more people there. Again, if you let us know, it would be appreciated. And the final one, before I hand over to Michael, is I've been asked by Jeff if I could make a bit of an announcement. Some of you will know about the Lion locomotive. Most of you will actually know it a bit better as the Titfield Thunderbolt. I think I'm right in that, Jeff. And the group of volunteers that have been looking after this are struggling. They are desperately looking for a number of people to volunteer. If anybody would be interested in volunteering to help with that group, please let me know and I'll pass your details on to Jeff. Okay.
Thank you, John. Well, welcome to Michael Bailey tonight, who's going to give a talk on progress in design and manufacture the steam locomotive 1825 to 1830. As John was saying, there's 100 people online listening to this talk, and there's 30, 40 people in the audience. Just a
Can't
few
hear
words-
you.
Just a few, can you hear me now? Yeah. Just a few words about Michael before he gives
Get nearer the microphone.
Won't be swallowing it if I. Michael Bailey is the past president of the Newcomen Society and is the current president of the Stephenson Locomotive Society. He is the chairman of the International Early Railways Conference Series. He has carried out considerable research into the early development of steam locomotives, especially non-comprehensive archaeological projects on behalf of museums in Britain and Canada, in conjunction with two fellows of the Newcomen Society. He is the author of several books and papers on early locomotive development. So, Michael, thank you for coming, and it's over to you. Thank you.
Right, thanks very much indeed, David. I'll try and speak so everyone can listen. Anyway, good evening, everyone, and especially good evening all those 100 people who have tuned in. That you'll find the this evening of interest. Now, the subject I'm covering this evening lasts just 5 short years, from September of 1825 to September of 1830. 5 dramatic years in which mechanical engineering took giant steps in design, in manufacturing, and in the selection of new materials. It was an extraordinary 5-year period. I shall include the results of several of the studies that I have carried out with 2 fellow members of the Newcomen Society, Peter Davidson and John Clitheroe, investigating the archaeology of a number of the surviving steam locomotives from this period. That's Killingworth Billy, the Hetton Lion, Locomotion number 1, Rocket, Invicta, and indeed some of the experience that I gained with the Planet replica locomotive at the Museum of Science and Industry in Manchester. So this is very much the story of Robert Stephenson and Company of Newcastle upon Tyne, because they were started up during this period, and they played a very large part, not exclusive, but very large part in this evening's story. Now I'm googling here to maintain. There we go. Right, now I'm going to start the story in 1821 to set the scene. This is an illustration which had been in the ownership of George Stephenson. Indeed, some people believe that it was actually drawn by Stephenson, but we have no conclusive evidence of that. And it shows the locomotive that he made for the Killingworth line in 1821. It was the last of the Killingworth type to be produced. It is much of the so-called Killingworth type of locomotive, which he had introduced onto the line in 1816, and which gradually increased in size and in weight as time went on. This was the largest of the fleet, and was possible by the relaying of the line from cast iron rails to wrought iron rails, allowed the increase of weight. It's a fairly simple design, as you can see. It's a simple, oops, we lost it there. It's a cylindrical boiler with a flue passing through from the rear, where the fire grate is to the leading end, leading up to the chimney, with 2 vertical cylinders set to the crown of the boiler, and the vertical action of the piston transmitted through heads guided by slide bars. The 2 cylinder actions are coordinated by the called stirring chain, which links the 2 axles together, to the 2 cylinders getting out of sync. So this is the latest design, if you like, at a time when the Stockton and Darlington Railway prepared both for Parliament and indeed for for George Stephenson to take on the engineering of the line, as he did in the subsequent months. The next illustration I'm going to show is the next development, which was the locomotives for the Hetton Railway in 1822. The locomotive is basically the same arrangement as that which we looked at just now, but smaller. And that was for a very good reason. That is because the Hetton colliery line was laid down with cast iron rails, with all the limitations that Stephenson had understood. He was one of the best parts of Stephenson at this time was understanding you don't design a locomotive, you design a transport system. So track and locomotive were progressed hand in glove. So the Hetton colliery, a contemporary illustration of the Hetton colliery locomotive, again with the characteristic that we saw in the earlier one. The other point, incidentally, is that we're not using any springs other than the so-called steam springs, which Stephenson had introduced on the Kenilworth line in the 18 teens. So they were still in use on the colliery line. We learned a lot about the Hetton colliery locomotives when we looked at the Hetton locomotive based at the Locomotion Museum in Shildon in County Durham. In anticipation of the startup of the Stockton and Darlington Railway, there clearly was demand identified for manufacturing railway equipment, including and especially locomotives. And so the Robert Stephenson Company was formed in June of 1823. At first, they undertook contract work for customers at the Bedlington Ironworks, because the manager there was also a partner in the Stephenson company. They purchased, leased land, I should say, just the 4th Street in Newcastle, and they began to build and fit out initial workshops between the October of 1823 and the August of 1824. To begin with, they had about 40 smiths, machinists, and fitters, and shortly after the work declared open and full use, Stockton and Darlington Railway ordered their first 2 locomotives from the company on the 16th of September 1824. They ordered 2 locomotives. The good news. Bad news is that they hadn't got a manager, because Robert Stephenson was in South America and George Stephenson suddenly became extremely busy because so many people approached him to undertake schemes for railways in various parts of the country, and he refused to say no. He kept saying yes, and therefore he burdened himself with an enormous amount of work. Okay, well, George Stephenson, but he wasn't on hand to supervise the beginning of the work on the locomotives. The railways that he was involved with were very much the Liverpool and Manchester Railway, of course, and the Liverpool and Birmingham Railway. And to begin with, he had to prepare all of the results of the engineering surveys and all the drawings for the parliamentary session of 1825. So to fill that gap, he looked around for others. Now, we are told that Timothy Hackworth came to join at that time. The trouble is, we don't know how long Timothy Hackworth was engaged at the factory then. Young tells us that he was there for a few months. James Kennedy was the other person that George Stephenson approached. He was a Scottish millwright who had quite a lot of experience with the fitting out of steam engines, which were marine engines on board various ships. And he was undertaking this work in the Liverpool and other northwest ports there. George Stephenson approached him and said that could do with someone of Kennedy's experience. Would he please come to 4th Street and undertake the work of manager to carry out the first orders that the company was receiving. So there, from that moment on, once Kennedy was installed, communication with Stephenson was by written word. This remarkable drawing survives in the Tyne and Wear record of it. It is not only the first locomotive drawing that we know of, but it is also particularly important because it is a pre-production drawing or sketch, I should say, of a locomotive. It's written in Stephenson's own hand, and one imagines that he also prepared all the sketches that you can see there. What he was trying to convey with this amazing drawing is that he would like to coordinate the action of the pistons by using parallel motion rather than relying on the surging chain that had been the case with the previous locomotives that we looked at. Kennedy was left to interpret what it was that Stephenson was seeking to do. Not an easy, you can't just use a sketch like this and suddenly produce a locomotive that fits all those requirements. The next drawing that has remarkably survived is another pre-production sketch. It was prepared in almost certainly 1824. Now, this is preserved in the National Railway Museum in York. It shows two alternative arrangements for parallel motion. On the left side is William Freemantle's grasshopper motion, and on the right-hand side is James Watt's parallel motion. There is no text that accompanies this drawing, or none that has survived. And so we are left to wonder who prepared it. It is my belief that it is prepared at Newcastle to send to Stephenson with the accompanying letter saying, which one do you want? Which presumably means that Kennedy was the drawer of this drawing. Now, it could have been Timothy Hackworth, but we have no historical record confirmed either way as to who produced it. The parallel motion was his attempt to interpret Stephenson's requirement. It does away with the surging chain and provides the link between the two driving axles with coupling rods. But there are no springs indicated. In other words, they sought to abandon the steam spring. Therefore, how would they overcome the problems of the uncertain track of the Stockton and Darlington line? You can see in the centre sketch on the underside of the boiler, this is a rear view looking forwards, that the axle is inserted into a sleeve, and the sleeve rotates on the underside of the boiler. In other words, the rear axle can rock down an inch or two in either direction to accommodate the ups and downs of the track. So that was to maintain the 3-point contact with the rails that obviously would be required to minimize the dynamic damage to the locomotive and indeed to the track as well. And so with this rather slim sort of evidence and very little in the way of words to accompany it, the story of the locomotive being made staggered on with a lot of uncertainty. And it certainly wasn't ready by the time we get to the January of 1825, when the Stockton and Darlington directors, quite rightly, quite understandably, said, how are our locomotives going? Are you getting on with them? Are they finished? And of course, they were far from finished. And so one imagines that for the two locomotives, that the first two boilers were made. That was fairly standard. That the wheels were cast, and very little else was prepared until Kennedy was able to make some sort of start, sort of guess at the use of the parallel motion. George Stephenson, by this time, was just inundated with work, not only Parliament for the Liverpool and Manchester, Liverpool and Birmingham, but also with other themes as well. In fact, he was so inundated, it was a kind of mini mania in 1825. And so he decided that he would need to form a separate company and engage a number of junior surveyors to undertake this work under his supervision. This is the beginning of the George Stephenson and Son company, which was formed in that month. All right, now we come to the interesting bit, which is what happened to the two locomotives that were being made for the commencement of operation on the Stockton and Darlington line. Now, the most recent study that I've carried out with Peter Davidson was on the what is now known as Locomotion 1 on the Stockton and Darlington, which we saw in the opening slide with its parallel motion. And we carried out 2 years' worth of research to understand what really happened to this locomotive, rather than what we've been told had happened to the locomotive when it was taken out of service. The locomotive now see as Locomotion number 1 is very familiar because it's always been like that ever since 1857. But now it seems that it had been rebuilt on 3 occasions. In fact, to be perfectly honest, there's nothing left of the original locomotive. It's all been replaced, as far as we know. There may be the odd nut and bolt, perhaps, but not a lot else. So the 2 locos, they've been made, say, with boiler and wheels, but the decisions were still pending. George Stephenson returned, perhaps one might say, with his tail between his legs, in June of 1825, following the throwing out of the Liverpool and Manchester Railroad bill at that time because of difficulties and errors in the survey of that line. So he came back to Newcastle and at long last to take over responsibility for the design of this first locomotive. Kennedy was struggling, as I say, and the Stockton and Darlington Railway desperate by that time because the line was finished. There was an awful lot of money in the railway. They wanted to get on and move the coal just as fast as they possibly. So Stephenson apparently, now we have no concrete evidence, or what the Americans would call smoking gun evidence, that he had decided to abandon the parallel motion and fall back on the known technology, which is slide bar guiding the crossheads. And this, we think, this is a drawing prepared in our recent report to the National Railway Museum. This, we think, is what locomotion looked like when it was first made in the summer of 1825. It's very much like the traditional Killingworth type, but for the fact that there are no steam springs. There is the rear axle in a tilting sleeve, and the coupling rods have been added on as well. So that's what we think it looked like. Now, the fact of the matter is, when it was sent to the Stockton and Darlington for that opening day on the 27th of September of that month, it worked straight out of the box. It was very successful. Thousands of people out because it was such a novel occasion, and they all wanted a ride. Lots of people jumped on and had a ride, but many thousands of people who were watching. Had it failed, it would have been a dismal failure, and he would have been distraught. But it wasn't. It worked a treat. Problems did arise after weeks of operation with the wheels. A lot of difficulty with the dynamic forces of the coupling rods and connecting rods and the rather spindly spokes that they had on these cast iron wheels meant that the wheels were working loose and cracking and so on. So, but I'll come back to that. Now, further illustrations of the opening day as sketched on the opening day, these are contemporary illustrations, suggest confirmation that slide bars and not parallel motion were used. You can see there clear indication of that the three respective artists had made an attempt, a good attempt, at showing the slide bars, and no question of guessing at what the parallel motion would have looked like. Now, you cannot take sketches and use that as evidence, but it is comforting to think that the guys who were there on that opening day actually chose to illustrate the locomotives in this way. So it drew about 80 tons and it carried about 700 passengers. These are the accounts of the day that we've fallen back on. It drew 30 wagons between Darlington and Stockton, and on its approach to Stockton downhill, it actually achieved 15 or 16 miles per hour. Now, a great deal of this success was down to George Stephenson's elder brother, James. James was an experienced driver who had been in the Killingworth, moved across to the Stockton and Darlington to set up the driving skill on the S&D, and no doubt chose to teach new drivers to supplement the work that he was doing to build a force of drivers for the growing railway company. Further evidence comes with this locomotive, which was made for the Mount Moor Colliery, County Durham, and remarkably survived until photographs could be taken of it, which were this photograph was taken in 1862 by Bleasdale. The collection of Bleasdale photographs in the NRM includes this one, and you can see there, locomotive made a few months after the first locomotive, and it includes no question of parallel motion. It's got the crossheads guided by the slide bars above the boiler, and also the fixed couplings as well. So it's a remarkable survivor in 1862 that allows Bleasdale to photograph it and to provide that confirmation. Fine, so far so good. Now we come to the second locomotive, and indeed the other ones, but let's concentrate on the second one. Now the second locomotive was finished in the November of 1825 and was a disaster because it did have parallel motion, and just here has made a brave attempt to illustrate what he saw, without perhaps fully understanding it, but nevertheless it was a very brave attempt and leaves us with some understanding of why the second loco was a disaster. I'm going to read to you two extracts from the minutes of the directors' subcommittee. The first quote is shortly after this loco arrived. I mean, just a couple of days. This committee feel very much satisfied with the manner in which Messrs. Stephenson and Company have delivered the last locomotive engine on account of its imperfect state. The smiths having been employed a whole week before it could be got to work. That's a pretty damning indication that was communicated to the Stephenson Company. And the second quote, just a week or two later, the directors indicated that Robert Stephenson and Company requested that in any engines they may furnish us with, not to send any engines with new and experimental apparatus, that such fitting up as has been tried and approved already. So they were in deep trouble because the geometry of the parallel motion had not been proved. Not only the geometry of that, but also if we take fairly closely what the artist has shown us here, that the valve motion driven by the connecting rod of the rise up from the center of the connecting rod is also fitted to the top side of the boiler in a way that looks questionable, to say the least. So they had a lot of problems. They managed to fix it eventually, but it left us a sour taste in the mouth between the company and the manufacturer. Now, this drawing has been prepared by Ernest Forward, who was the curator at the Science Museum in the 1920s and 1930s. He did a lot of research into the early locomotives, particularly numbers 3 to 5. There were 5 locos in all. His best interpretation is shown in this drawing, which was published in the Engineer in October of 1941. Now, he's indicated some of the wheel improvements. I'll come back to that subject. He's shown the tilting sleeve for the rear axle and various other components, which more or less fit in with what we now see on the locomotive as it has survived. The reliability of locos was totally dependent upon the drivers and the maintenance men. James Stephenson again led the way. He managed to drive not only the first locomotive, which, by the way, was known by all the drivers as the Active. That was the name. It didn't carry that name, but certainly the drivers called it the Active. And that was a name that stuck all the way through its working life, right away through until its preserved life. It was always known as the Active. Eventually, in 1827, it was actually given a number because the fleet was starting to increase, and they couldn't refer to it obliquely. They just started to give numbers, which is a simple way of overcoming the problem. Now, the second locomotive, the one we were looking at just now, that had a serious boiler failure in the tail end of 1827, much so that the flue was very badly damaged, and so also was the boiler, so much so that it was withdrawn from service. So that left 4 locomotives, and when the railway eventually came to name the locos in 1833, I should say, then the locos that survived, the first one, of course, was called Locomotion. The second one was called Hope. The third one, Black Diamond. And the fourth one was called Diligence. So the important point about Diligence is that it was taken out of service in 1833 and was heavily rebuilt by Timothy Hackworth. So much so that it was virtually a new engine. So the boiler was laid aside at the Shildon Works, complete, and we have this from the inventory, complete with its parallel motion. And it seems that in that year, Diligence boiler was put back as the third boiler on Locomotion. That's something we've learned as a result of the study, the recent study that I referred to. The fact that the original boiler has not survived actually is not too bad when you think that the boiler made in 1827 was put on it, and that is one that survives to this very day. So to have a boiler dating from 1827 surviving is truly remarkable. So we learned a great deal about this boiler and the way it was made. Sadly, we're not allowed to look at the outside plates of the boiler because allegedly it has got asbestos dust. Heaven only knows where the dust could have come from, but that is what was said by the NRM. Therefore, we had to live with it and therefore examined the boiler from the side. And it's that difficult. You have to bury your head inside the boiler and use a telephone camera on a selfie stick. Believe you me, that's very difficult to do, to gain as much knowledge as we can about the formation of the boiler. Now, this view center of the illustration is the crown center line, and the left and right sides are the bottom center line of the loco. So the whole thing has been flattened out so to illustrate the formation of the boiler. Now, the method of construction was that the boiler plates were longitudinal, and with each ring, as it was built up, the plates were riveted to the outside of the previous edge. And it was gradually rolled and new plates riveted. So you get this progressive, I hesitate to call it cylinder, because by the time you've overlapped 7 times to go round, it's not cylindrical. And that really is the point. It was a peculiar shape, not cylindrical. And therefore, nothing fits precisely. For example, the flange of the cylinders is set into the crown of the firebox there, and it overlaps, and therefore nothing fitted precisely. So there's the crown plate is curved, but also overlaps. And so the fitting of the flange had to be achieved by placing it as near to the boiler as possible, but then filling with filler between the edge of the flange and the actual boiler plate. And that was pretty evident, though we didn't get down, see the exterior part of the boiler. Nevertheless, we were able to understand the difficulty that they had in fitting the cylinder flanges. The plates were 14 plates in all, between 1'9" and 2'6" made. You try to imagine taking that boiler by progressively adding on the outside of each plate as you go round, then you've got very limited headroom inside for the little chap to place rivet so that the riveter on the outside can close that rivet. Now, looking at the Stephenson Works archive, the archives, it is evident that they employed young lads of between 14 or 12 and 14 to pick up rivet, place it in the hole, and then for the riveter to close that rivet. So, poor young lad must have lost their hearing at a very early age. It doesn't bear thinking about, but that's the way they did it, seemingly. Now, so much was the initial engines that by the time we get to the November of 1827, a new form of locomotive appeared from the Stephenson Company. There's very little in the way of paperwork to accompany this drawing. It could be that Timothy Hackworth initiated this different approach, because it was fundamentally different. The cylinders are buried into the rear plate, the rear plate of the boiler, working horizontally rather than the twin cylinders in the crown, as we saw previously. So the whole geometry is totally different, and the drive is on the leading axle only. The rear axle is a axle which is coupled to the driving axle. Fine, this was all very well, but when it was delivered, it was found to be too heavy. It was too ambitious. And the Stockton and Darlington, and with Timothy Hackworth in particular, had to decline the engine and ask for it to be taken back and rebuilt a third axle. And so it operate for very long before they reached that conclusion. Now, I should say that throughout these early years, there were difficulties with the weight of each of the locomotives, and also with the state of the track. It needed a great deal of maintenance. It was being punished by the action of the steam locomotives. So that takes us to the end of 1827, and then a remarkable event took place, and that is that Robert Stephenson came home to America. George Stephenson, his father, was so pleased to see him because he could take over from his father the development work of the locomotive so desperately needed. And so, having shed himself of his concluding responsibilities from his work in South America, from the January of 1828, he took on from his father the responsibility for developing the locomotive for the forthcoming mainline purposes, in addition to the freight purposes on the Stockton and Darlington and the railways. Robert Stephenson, a very, very talented engineer, began what today we would call a research and development program, in which he would investigate each aspect of the locomotive on its own and try to improve what it did and how it did it. This is in marked contrast to his father, who always took an empirical move to try and improve things. George Stephenson would say, if it works, well, do it again, but do it bigger. Whereas Robert Stephenson said, how are we going to improve the locomotive? No sooner that he'd started, they received an order for 2 locomotives from France. So here then was the opportunity to try out some of the ideas that Robert Stephenson had in his mind. Now, these 2 locomotives were for Marc Seguin, the engineer from the Lyon part of France. He was the engineer for the coal line near Lyon. And the locomotive, again, is so completely different. So Robert Stephenson had obviously sat down and had already said, why don't we try this? Why don't we try that? Let's see what we can come up with. The obvious changes are it's only a small locomotive, but you can see there that the 2 cylinders are now in the midpoint on either side of the loco, and with parallel motion acting on the 2 driving axles, which are also coupled. So you get a kind of parallel motion. The wheels also are interesting because they have changed from cast iron to wood. Now, that's a big, bold step. Is wood going to be strong enough? Well, he obviously called in experienced wheelwrights to make the wheels. They had an understanding from the years and years of understanding of work for the road vehicles that they had built up. One of the main problems that has also been featured on 1 or 2 of the other locos that we've seen earlier this evening, and that is that the crank ring had been added to the wheels to strengthen the forces on just a single part of the wheel, so that the forces are taken round the wheel rather than just in one particular point. So the loco is much lighter. That was important, because some of the earlier locos on Stockton and Darlington were getting really very heavy. The next loco that Stephenson had the opportunity of making and trying out his ideas was with the loco that was destined originally for the Liverpool and Manchester Railway, but subsequently went to the Bolton and Lee Railway. This is the Lancashire Witch. And the Witch has introduced something which is brand new and very important, and that is plate springs. Now, plate springs had been first used on the Killingworth wagonway. They were tried out on one of the wagons there to see how they worked and how robust they were. They did work, very successful. In fact, so successfully that the first person who asked to go and see them was Timothy Hackworth. And we even have his expenses claim for going there to Killingworth to see the plate springs. And they were adopted by the Stockton and Darlington Railway and also on the Lancashire Witch. The locomotive here has two flues, not a return flue in the way that I'll explain just coming up, but that two quite distinct flues in parallel with each other. And the flue gases were gathered together in at the front end, were gathered into one bulbous chamber that fed then to the chimney. Again, it's got wooden reels with the wooden with the wrought iron crank ring, and this locomotive was also the opportunity for Robert Stephenson to try out other experiments as well, even to include expansive working. Now here we're jumping ahead. There's been previously no consideration of expansive working up until this time. It wasn't overly successful, but nevertheless it shows the sort of ideas that Robert Stephenson was playing with. Now, no sooner had the Lancashire Witch been made than there was another order received, this time from the United States, from the Delaware and Hudson Railroad in Pennsylvania. And this loco, very similar to the Lancashire Witch, was given the name Pride of Newcastle. Heaven only knows if it ever carried that name, but that's what is now being referred to. And so this particular drawing that you're looking at has also survived, and serves to introduce another particular point. When Robert Stephenson came to Newcastle to start off this research and development work, he engaged George Phipps, who was a draftsman. So for the first time, the company, the design of locomotives was handed to an individual who was going to draft out various arrangements for the locomotive and calculate their weight, importantly. So George Phipps became an important part of the Fall Street team. The other person that I've got to mention, because he's so important, and that is William Hutchinson, who was the leading foreman at the Newcastle factory. In fact, I think today we might call him the works manager, but he really was a very experienced man. So he was able to carry out some of Stephenson's ideas by saying to Stephenson, you can do this, I can manufacture this, but I can't manufacture that. We can do this, we cannot do that. And the three of them, as the designer, the leading foreman, and Stephenson himself, formed a kind of triumvirate for all this development work. And this is some of the fruits of their work. Now, another most important part of the story, we've got to take a step back to the November of 1827, to the work that Timothy Hackworth was doing. Now, Hackworth was the locomotive superintendent of the line, and therefore responsible for the engineering of its locomotives. And a locomotive was offered for trial from the outset of the line in 1825-26. And this was a locomotive built also in Newcastle and was known by the men, I suspect, by the sort of noise it made. It's called the chitterprat. It was unusual in as much as it had 4 outside cylinders. It kind of worked, but I think the maintenance on maintaining this was a bit excessive. And so Timothy Hackworth declined to accept it, but kept the engine. I don't know what the arrangements were, but he kept the engine. And what impressed him so much was the boiler, because the boiler had a return flue, and therefore this increased the heating surface that was available for use with the loco quite considerably. So what he said is, right, I'm going to use this boiler. I'm going to extend it by adding another ring to the front end, and I'm going to place it on 6 wheels rather than the 4 wheels that the chitterprat had come with. And so this is the loco that was drawn at the time. You can see the return flue arrangement that it's got there. You can see the vertical outside cylinders, and you can see also there's something else that he borrowed off the chitterprat, and that is the two-part wheels. Now, I mentioned before that the wheels were giving trouble. That's the cast iron wheel. And so the way around it that was picked up by Hackworth and developed, and in fact has become known as the Hackworth wheel, the two-part wheel with a center, still with the spokes, but with a reduced diameter, and with the external rim that was fitted over that center part. And the two were fitted together using oak plugs. So this was much more robust, but it also had the advantage that if any cracking appeared in the cast iron during its operation, that component could be replaced much quicker than having to take the whole wheel off. And so the Royal George, as it was called, became a much more powerful locomotive than the earlier Stephenson locos. Now, all this is by way of introducing what happened to our old friend, the Active, the locomotive that started the Stockton and Darlington line. Because in the July of 1828, the boiler failed badly. The flue and the boiler barrel were badly damaged, and sadly, the driver, John Cree, was killed. This was on the 1st of July, 1828. So Hackworth then had the decision to make. What should he do with it? Should he just scrap it or try something else to replace that badly damaged boiler? He decided that on the basis of the increased heating surface of the Royal George, that he would replace the boiler on what had then become number one and replace it with two return flues. Now, this really is brave because, yes, you get a much increased heating surface, but somehow you had to understand how to fit two return flues into the boiler. There wasn't much room. The original boiler was 4 feet in diameter. And so he went to Newcastle for discussions with the Stephenson Company, or no doubt with the boilermakers themselves, and said, this is what I want to do. And they played around with it for quite a little while and came up with the idea of putting on a replacement boiler, which was slightly larger, 4 feet 6 inches diameter. And this enabled them to have enough room inside the boiler at the return end of coming back with two return flues. And it's in this form. This is the way that Peter Davidson, who prepared all these drawings, it shows how it could fit within that diameter boiler. Now, we know all this because the Stephenson Works records carefully record the weights and components of the flue, the return flues, and the chimney. They're all recorded so we could work out not only the arrangements, but also the weight of the replacement boiler. Now, it's strange, of course, strange to our eyes, because the loco now has two chimneys. Now, if it had two chimneys, that means you've got to have two blast pipes. And so Locomotion, as we now call it, was fitted with two exhaust pipes, one to each of the chimneys. It ran for about 3 or 4 years, and was successful. We were able to record how much coal month by month that it hauled, but it was in fact still very heavy. You can imagine a bigger boiler, bigger diameter boiler, and two return flues. It was very heavy. And so they decided in 1834 to remove this boiler and put on it that boiler that I mentioned before that came off the Diligence, and is the one that is now surviving. But in so doing that, they left on the two exhaust pipes. And the two exhaust pipes fed into the single chimney of the return flue engine as it became. And those two exhaust pipes survive to this very day. It seems that no one's ever thought to ask, why has Locomotion got two exhaust pipes? And that's the reason. Right, let's take the story on a bit further. The experiment, as the loco we saw earlier, was subsequently rebuilt onto three driving axles. It was fitted with two-part cast iron wheels and then operated more successfully this time because it didn't tear the track to pieces. So that locomotive was eventually an important part of the fleet of the Stockton and Darlington line. As time moved on into 1829, then, of course, other orders were taken, and the benefits of the new knowledge that they had gained started to be incorporated. This, again, is an original drawing that survives in the Tyne and Wear Record Office. This is travelling engine number 15 for the Tredegar Iron Company in South Wales. It has a return flue. It has the plate springs, and it has the cylinders now for the first time fitted to the side directly onto the leading axle. And the important point here is that with springs, it can accommodate the direct transmission in this manner. The wheels are the two-part cast iron wheels, which it carried. But now you'll notice that I'm jumping from one activity to other activities. If there were two production lines in the factory, one was the progress being made with the traditional coal-moving engines, and the second production line was with the experimental engines destined for the Liverpool and Manchester railway. So in addition to this sort of locomotive that was being made at one part of the workshop being made, then we move on to further locos that Robert Stephenson was very much involved with. He looked at steam generation, as we saw earlier, but on this particular occasion, he looked at the sort of boiler that had been employed on some of the steam vessels, again, over in Liverpool. He approached the William Laird Company of Birkenhead and obtained some ideas for these small vertical boiler locos. There's two boilers side by side there with two chimneys and two exhaust pipes and so on. So there it is, fitted with plate springs and wooden wheels and wooden and iron crank rings. That was known as the Twin Sisters. And just out of interest, we have this delightful picture of the Twin Sisters on the Liverpool and Manchester line. I suspect rather exaggerated in height, but nevertheless, it gives you a good impression of what the sisters apparently look like. It's a very decent image, including the large barrel on the tender. In addition to that, another vertical boiler, marine engine type boiler, was put on another engine. This was for the William Foreman of South Wales in Penydarren, and not quite the same in the way it's been portrayed, but nevertheless the principle is exactly the same. And you've got a better indication there of the plate springs, incline cylinders, and the crank rings as well. Now, in the next locomotive was, as it were, one of the traditional runs. It's a locomotive for a mineral line. It was for the Stockton and Darlington. It was named Rocket, which is interesting in itself. And it had a return flue, plate springs, direct transmission again, two-part cast iron wheels. And in addition to the Rocket, which was duly delivered to the Stockton and Darlington, the next engine was also a very similar arrangement as the Rocket, and it was travelling engine number 17, which was built again for the United States, for the Baltimore and Ohio Railroad. Now, I'm very attached to this engine because several years ago, I led an expedition to try and find it, because on its delivery run from Newcastle to Liverpool, before going across the Atlantic, the ship sank. And I assumed that the locomotive had been taken down to the bottom of the ocean. Well, in fact, further research afterwards, after leading the expedition, it transpired that the components of the loco were rescued with using a Bridges Buoy affair, and the components brought back to the seashore of Peterhead in Scotland, and were returned to Newcastle. But nevertheless, this is a very interesting. Sadly, all of the components were thereby lost, and the boiler, in fact, was used in the factory itself for a number of years. But the main activity in 1829 was a much lighter locomotive that was built in anticipation of the Rainhill trials. Now, Robert Stephenson headed up the consideration of the design for the rocket, with George Phipps doing the necessary drawings, and William Hutchinson undertaking the necessary manufacture and using all his experience. They were weight limited to 4.5 tons for the locomotive. But the most important feature, of course, as we know, is that instead of a return flue or a twin parallel flues, that's the suggestion of Henry Booth to use multiple small tubes, was accepted. Now, Booth is always known to have suggested the use of multiple tubes, but it's one thing to have a notion, it's another thing entirely to carry it out. Because just imagine, oh, by the way, why don't you just use multiple tubes and a tube plate? But then you make it work when it's never been done before. That was the challenge, and that's where William Hutchinson came in. Yes, they eventually made a watertight boiler. They had to put in 3 different kinds of stay inside the boiler to prevent it expanding unduly. And of course, having made yourself a steam-tight boiler, you then got to think of, well, where do I put the fire? So they had to invent, in inverted commas, the firebox. Now, the firebox, Stephenson reckoned, should be in copper. I mean, much more efficient in copper and less with less corrosion than it would have been with a wrought iron box. Where do you make something out of copper plate in 1829? There was very little opportunity for using copper plate then. Copper sheet, yes. And in Liverpool, they had the best executors of copper sheet use in the country. That is by placing the copper sheet on the bottoms of sailing vessels. And so they went to the coppersmiths in the Liverpool docks and said, we want a firebox made more or less in this sort of presentation, which was a 2-part box that enclosed the water within it and riveted at the edges. Made that box by hand over a former. They made the box, they sent it to Newcastle to fit on the vehicle that was then making, and it didn't quite fit. It was just a little bit out of true. And so we know precisely how much it was out of true because John Clitheroe and I examined the rocket very, very carefully when we undertook the archaeological work on rockets, and we know precisely how out of true it was, and how they jiggered it around a bit to make it fit because they hadn't got a lot of time available. It also used a wooden driving wheel, or the 2 driving wheels were wooden. Of course, they used the plate springs. The other significant change which was made at this time was the use of coke rather than coal. Now, this is a major change brought about by the Enabling Act of the Liverpool and Manchester Railway, which necessitated not having engines that smoked. And so this was all part of the crucial design of the firebox for the vehicle. It also used a slip eccentric method of changing gear from forward to back, but no question of carrying on with the ideas that Stephenson had of expansive valve gear. That was too complicated for this time. It had to be rebuilt this is rocket we're talking about. It had to be rebuilt after a few months because the danger when it was going downhill, down the Western Incline, Rainhill Incline, that the water would surge forward and away from the crown of the firebox. And so they rebuilt it with a dome. Now, the rocket is usually shown with a dome because it's an integral part of our understanding of rocket. But in fact, it didn't have a dome at the time of Rainhill. That was put on in a few months later. And that dome allowed the water level to be raised significantly to allow the locomotive to operate with more security, that the crown of the firebox would not be exposed. So an examination of the boiler of rocket is itself very interesting. Now, this is a drawing Leatherow did for our report a few years back. It actually shows it as it is now. So for the moment, ignore the smoke box at the leading edge. We just have to look at the boiler of rocket and how the firebox would have been had it survived. The important thing here is that the iron boilers from the previous generation of locomotives was abandoned. And the reason for this, we now realize as a result of the Locomotion study, is that the quality of the wrought iron was very poor. It had 7, 8, 9% impurities within the wrought iron, which made it, which would have contributed to some of the failure of the boiler that had occurred on the Stockton and Darlington line. And so what Robert Stephenson decided on was to obtain boiler plates from Staffordshire instead of from Bedlington. And the design of the boiler now has rings rather than horizontal plates. So you've got two rings here, and the two hemicircles, if you like, for the boiler plates were placed one above the other, butted on top of each other. And to secure that, there was a strap run along the join, you can see in the center of the boiler there on either side. And that's a form of button strap type of boiler worked very well indeed. And well done to William Hutchinson for achieving this design of boiler using techniques which are so new that he was able to put it into practice just by intuition. And the firebox, of course, was added on in the way that I've just been indicating. So we all know what happened. Rocket won handsomely at Rainhill. And as a result of that, the Liverpool and Manchester Railway then decided to order, first of all, 4 more locomotives from the company. Learning from the prototype rocket, they decided that the subsequent 4 locos, the geometry of the driving motion would be altered, so the cylinders are lowered right down to near horizontal rather than at a diagonal form. They too had a button strap boilerplate, so you can see the strap exposed there on that drawing. This drawing has survived in the Tyne and Wear archives. Again, wooden driving wheels, although the crank ring has been rather strengthened there, suggesting they still had problems with the original wooden wheels. Now, these 4 locos were called Meteor, Comet, Dart, and Arrow. Now, I think it was with either Dart or Arrow that they carried on making trials on the Liverpool and Manchester line. This is the beauty of this close association between Robert Stephenson and Company and the Liverpool and Manchester Railway, because the company used the railway as a test bed to try out innovations on the locomotives, and giant steps were made as a result. So with Dart and Arrow, they decided to see how they could improve the climbing of inclines, because they were anticipating severe difficulties with the next order that they had received, which was from the Canterbury and Whitstable Railway. Now, this drawing on the left-hand side is a drawing which has survived, one of George Phipps's drawings, which has survived in the National Railway Museum. In fact, there are two drawings like this. Now, the bottom right-hand corner is Invicta, as we now see it, and as we've come to get used to. But in fact, it has been much rebuilt. And so we need to try and understand from the drawing on the left, but also from this remarkable model in the top right there. This model, which was loaned to the National Railway Museum at its exhibition a couple of years back, is in fact closer to the original than we could have understood from the drawings alone. The model was owned by Edward Fletcher, who subsequently became the chief mechanical engineer of the North Eastern Railway. He it was who was an apprentice at the Robert Stephenson Works. He brought Invicta to Whitstable, and he and subsequently trained the drivers that were to take it over from the time he left. Now, what we can see there is a locomotive which is very similar to the rocket and the modified rockets, but it's a four-coupled engine with connecting rods. Now, the reason for this is that it had to climb the steep incline from the harbour in Whitstable up to the upper level of the line before it proceeded on its way south to Canterbury. And so it was quite a demanding challenge to enable the locomotive to achieve that. So again, we are blessed with a set of drawings and this wonderful model to have worked with. Now, one of the interesting points we found on the study of Invicta was that George Phipps had tried to achieve an improvement with the valve chest and the slide valve. Instead of achieving a short, instead of having a long steam passage to both ends of the cylinder, he tried to foreshorten that because it's extremely difficult to cast a casting with a long steam passage. To get the core out from after casting is exceptionally difficult. So he tried to make, instead of a short valve movement, he tried to make a long slide valve. As you can see, first of all, on the original drawing, that's George Phipps's drawing on the top right there, and then Peter Davidson's drawing at the top there is how he has interpreted what Phipps was trying to do. You can see there that therefore, if that was to have worked, it would mean that the steam passage would be relatively short and much easier for the foundry than it had hitherto been. The trouble is that once the steam got into the steam chest, of course, it clamped it down so hard that it couldn't operate very well. So that didn't work. And therefore, rather than waste time and waste money, he took the original cylinder, as you can see on the bottom there, and put in an additional casting, specially made with the steam passages in it. And that was only revealed as a result of the work that we did down in Canterbury. And therefore, it started life with a short travel valve. Now, in the right-hand side, we come, just jumping ahead a few weeks, we come to the Northumbrian locomotive, which has been shown with a long travel valve there, suggesting they managed to overcome the problems that they had with Invicta, but again, without the detail that we can't understand too much about that. So development work carried on the Liverpool and Manchester Railway rapidly through 1830. The first thing that they did was to realise that the bulbous front ends of the loco could be much improved by putting in a proper smoke box, which was a vacuum chamber good enough for the exhaust to pull the air through the tubes and to stimulate the fire in the firebox. Again, we've got on the North Star, we've got the external firebox still being fed to the boiler itself with tubes from the crown. We've got the wooden driving wheels and the near horizontal cylinder action. There are two locos made then, the Phoenix and the North Star. And the next loco, very soon afterwards, these were coming off the production line so quickly by now, all because of the work that Stephenson, Hutchinson and Phipps were achieving. And this time, with the Northumbrian, the firebox was incorporated within the boiler. That was a big step to take out those external pipes and the heat losses that would have resulted. They added on the boiler to that, added on the firebox to the boiler barrel, and also, of course, with the smoke box at the leading end. Also, the framework has been considerably strengthened because the additional weight would be involved. The weights had to be very carefully balanced for the locomotive to operate satisfactorily. And so that was the Northumbrian, which was finished in August of 1830. There was a subsequent locomotive, the Majestic, but that came along after the next locomotive, which was a remarkable change in the design that had been achieved by the triumvirate. The Stephenson looked at how the locomotive could be improved. There's all sorts of stories about the crank axle on this locomotive not being original. It was pinched from Hackworth's Globe and one or two other locos. But in fact, this must have been planned well in advance because of the manufacturing difficulties that they had to overcome. The cylinders were placed from the rear to the front. That was the first change. And that meant that the driving wheel was removed from the front to the rear. And the carrying axles obviously correspondingly went to the front under the smoke belt. Now, the cylinders were inserted at the base of the smoke box, and thus, again, from a thermally efficient view, it was much improved. Side motion was all very well, but it did require the manufacture and machining of the crank axle, and that was the key. So William Hutchinson it was who had the task of working out and achieving how to manufacture, how to forge, and how to machine the crank axle. It must have taken weeks and weeks. You could not do this very quickly. How to set up with the rather primitive machine tools that he had at his disposal, and yet he managed to work out how to do this and achieve it by the September of 1830. Now that machining takes some thinking about. Those of you who are have experience of machining, if you think about what they had available in machine tools at that time, that really was quite a challenge. In the center of the axle is the slip eccentric, which was achieved on the Planet. Now this takes some understanding. We did understand it in Manchester when we came to design and make a replica locomotive, full-size replica. We got it to work well indeed. It requires a axial movement of cluster from left to right. You can see there the dogs. You either engage the dog for forward motion or slide it across and engage the other dog for the reverse motion. It takes some doing, but nevertheless, it does work. The other thing that they improved no end was the introduction of a much superior frame. And this was a frame made from oak, plated on either side with wrought iron, the so-called sandwich frame. The inside frames were wrought iron, but the sandwich frame became a stalwart with subsequent designs of locomotives for many years afterwards. And so the Planet arrived in Liverpool on the very same week as the opening of the line on the 15th of September 1830. Now, Stephenson had made the promise that he'd have a developed steam locomotive available for the opening, but didn't quite make it. It was finished on the 3rd of September, put on board a ship, raced around Scotland, down into the Mersey, and was still on board ship on the 15th of September. But it was a damn good effort, nevertheless. And here is our replica at Manchester, and we learned a great deal about the early design of Planet as a result of this manufacture. We're indeed very proud of this locomotive. Well, we have it. 5 years from the active on the Stockton and Darlington Railway, and 5 years later we have Planet on the Liverpool and Manchester Railway. It is a truly remarkable piece of mechanical engineering history, and Robert Stephenson part in it. He came home and he worked on all the improvements that we discussed. In just 3 months, he produced Planet. That is an incredible piece of engineering history. Very much indeed.
Well, thank you, Michael, for that wonderful talk. It was absolutely brilliant. Thank you. Michael's agreed to answer questions from the audience. So if anybody's got a question.
Did none of the locos have brakes?
Sorry?
Did none of the locos have brakes?
Oh, the brakes. Well, they were only too pleased to be going, let alone to stop. So brakes were not overly important, but the tenders had screw-down brakes. So there was no question of having any brake from any speed. But what they used to do, of course, was to shut the regulator, put the locomotive into reverse, and then open the regulator again. And that counter pressure braking would slow it down if you knew what you were doing. But the crews at that time were very good at being able to stop the locomotive. This is on I'm talking about now the Liverpool and Manchester locos. On the Stockton and Darlington, the earlier ones, you just shut the regulator and all the resistances of all the moving parts slowed you down relatively quickly, because they don't go very fast anyway. The Stockton and Darlington speeds were something like 5, 6, 7 miles an hour. And they were pleased to be doing that. But brakes, no, you didn't worry about things like that.
Another question?
You mentioned that the Liverpool Manchester Railway was used as a bit of a test bed for development.
Yep.
Obviously that wasn't available till the later part of this era you're talking about.
Yes.
Was there something more local? Do you know that used at all? Or?
No, the Stephenson factory was very compact and had no means of testing the locomotives, with the one exception that when Rocket was completed prior to going round to Rainhill, they took it to Killingworth and tested it there on the Killingworth line. Now, this is one of the advantages of the Stephensons and their association with Killingworth. They were able to test things out like that. They made some minor adjustments as a result. So they took it back to Newcastle, made those adjustments, and then shipped it off to Liverpool. But what with Rocket? Oh yes, it's quite well documented. The locomotive performed exceptionally well, both on the Killingworth line before the trials, and then during the trials, of course, we've got detailed speed records of what it achieved. But the overriding thing is that the very final day, George Stephenson, as it were, flush with the success of the locomotive at the trials, he said, right, remove the load, remove any, he's not going to draw anything, just light engine. And they ran the light engine from one end of the test track to the other. And they achieved, was it 30 something miles an hour? I think it was 35 or something. And of course, the crowds were still there, lining the track, looking on, and they were amazed. And in effect, they were saying to themselves, this is going to take over from the horse, because the horse could not sustain that sort of speed for very long in these short bursts. And so what we're witnessing is a new era of transport.
Michael, what did you know about the science of steam? I mean, all of these were steam driven.
Well, right.
What did you know about it?
They didn't study it in the form of science. They studied it on the form of, we'll try it, see if it works, and if it works, we'll improve it.
Right.
It wasn't until the French engineer Chevalier de Pambour came over and then started measuring the performance of the locomotives in a number of different ways, and then committed it to a book in the early 1830s. That suddenly there was an understanding of what they were achieving with the locomotives, but it wasn't until then that they had any academic understanding of the science.
So it was all based on trial and error.
Yes, yes, it was.
If it worked, it was okay. If it didn't work, do something else.
That's right. Yes.
Yeah. Thank you. I think there's a question, John, online, isn't there?
Yeah, we've got some questions and some comments.
We have a number of questions and comments. I'll try to go quickly. From Richard Udin, sounds like Hutchinson was the real genius, made nebulous things actually work.
Yes, I've got nothing but admiration for William Hutchinson. He was an absolute stalwart. In fact, Robert Stephenson once called him the Oracle because he had such respect for him. And Hutchinson, in due time, in the late 1840s, went on to become a partner in Robert Stephenson and Company. Worked for someone who was a machinist and then a foreman and then a senior foreman. To become a partner was a remarkable accolade for him.
Chris Hodderan, a brilliant talk on some very brilliant and hectic engineering development. Please say who was responsible for the parallel development of strong wrought iron rails.
Strong wrought iron rail. Right.
The rail development. Sorry.
Yes. Okay. Well, there were one or two engineers, but in particular, it was the engineer working for the Bedlington Ironworks who developed the rolling machinery to be able to roll the rails to provide the wrought iron rails. Now, his name was Blenkinsop, and he deserves a lot of credit. And his rails were taken up generally, but in due time, very quickly, other ironworks started to be able to roll rails as well. So it was a very fiercely competitive industry because as the railway system developed, the market was enormous. And so the rails were, became a very large industry.
Derek Hawkes, question, what impact did the choice of coal have on the design and performance?
Well, the coal was available on the Stockton and Darlington as it was on the Killingworth line and all the other lines. So it was the obvious choice of fuel. Okay, it was dirty and smoky, but those days global warming hadn't been thought of. But when it came to the Liverpool and Manchester Railway, then they were quite specifically understood that a smoky environment where on a line that was to carry passengers as well as goods would not be acceptable to the passengers, particularly the ladies. And therefore, they inserted in the Liverpool and Manchester Act of Parliament that all locomotives should consume their own smoke, unquote. And hence the necessity for Stephenson to direct that what they were developing in that research and development program I was outlining, that the necessity of burning coke rather than coal Now, this increased the costs of railway operation quite significantly. And thereafter, for the next 20 or 30 years, every effort was made to try and reintroduce coal instead of coke to reduce the expenditure. It wasn't until 1857 that the redesign of the firebox with the brick arch enabled the coal to be the burning of the coal to improve, so that the amount of smoke was correspondingly reduced.
I'll try to do the next 2 or 3 questions quickly. Peter Jarvis, Mark Seguin, multitubular boiler, came to look at Menai Bridge, talked to Henry Booth. I think that's a comment. What was a typical early train wait on the Stockton and Darlington?
On the Stockton and Darlington, right. Well, that opening day load was about, what did I say, 70 tons. So that was abnormal. Normally, they would have about, it started off as about 20 wagons of coal, and then moved on to 24 wagons of coal, with the improvements in the track, so that the locomotives, as they became more powerful and heavier, and the track improved, then they went up to 24 wagons. Now, in the report that Peter and I wrote on the locomotion inquiry, we list precisely the tonnage of the coal that was moved by locomotion each month of its career. I mean, there were some gaps, of course, but for ostensibly it's month by month. And it is remarkable how many thousands of ton miles were achieved by the locomotive at that time. It must have been very satisfying for the directors to have achieved such progress.
Okay. There's quite a few just come in. Can you say anything on the early standardization of track gauge, which allowed the test on the Liverpool and of locos to be used elsewhere?
Oh gosh, gauge is one of those subjects you could spend a whole evening on. Well, the infamous standard gauge precedes the steam era. It goes right back to the wooden wagonways of Northumberland, and the recent archaeological digs on the wooden railway system, wagonway systems, has revealed that there were quite a number of lines that were made to the 4 foot 8 inch gauge, including the Killingworth wagonway. Now, this was determined by the width of a horse, basically. If you've before you had steam locomotives, you hauled the wagons by horse. So you have the girth of a horse and the chains or coupling rods from the horse to the wagon, and that largely determined the gauge. But of course, there were all sorts of widths of horses, so therefore different cars had different wagonways with different gauges. But anyway, George Stephenson agreed to settle on 4 foot 8 inches for the Stockton and Darlington Railway, and the early locos were correspondingly made to that gauge, and that persevered. So that when George Stephenson was responsible for laying down the Liverpool and Manchester Railway, he said, look, one of these days, all these railway systems are going to be linked together. So we've got to go for a standard gauge, hence the name. So they started off laying down the Liverpool and Manchester Railway with 4 foot 8 inches. Question, why the extra half an inch? Well, we can always argue about this, but apparently as the locos and the rolling stock started to be placed on the Liverpool and Manchester, they were too tight on the curvature and the point work and so on. And so it was easier and cheaper to expand the wheel sets, expand the track by half an inch than it was to expand the wheel sets by half an inch. And so you get your 4 foot 8.5 inches. Other railways in other parts of the country, in Scotland and so on, and certainly overseas, there are all sorts of different gauges because they started with all sorts of different horses. So you had everything from 4 foot 6 to 5 foot.
Two very quick ones. One's a comment. John Wilcox, quite interesting that some of the drawings were in third angle orthographic projection rather than first angle.
Yeah, well, that's because John Glidrow is such a good cartographer, well, not cartographer, a good draftsman, that he was able to do it in the isometric view.
Okay. From Chris Tuthill, were there parallel developments by Bury in the later period and Hackworth at Stockton and Darlington? Are Stephenson simply a long way ahead, or did they benefit from being well documented?
Yes, well, there's all sorts of arguments about who invented this and who did this first. Bury was a great one for copying what had already been learned, particularly because Kennedy, who had left the Stephenson factory, and I might have added in my talk about the time that James Kennedy left the factory at Newcastle. This was just after the catastrophe with the parallel motion on locomotive number 2 on the Stockton and Darlington Railway. We just don't know the circumstances under which Kennedy left. There's no paperwork, but it would seem that he disagreed with Stephenson or vice versa, and therefore Kennedy walked out, leaving the factory managerless. And what we do have is a letter written by George Stephenson to another ironworks, this time in Manchester, saying, do you have anybody who I can recruit, the cheek of it, I can recruit to become the manager of my works in Newcastle? I don't know what sort of answer he got, but he couldn't find anybody. And it was then that he spotted that William Hutchinson was coming up with all sorts of ideas. And it was quite clear that Hutchinson would be the man to become the senior foreman of the works.
This question
Yeah.
here,
A very, very basic one. Very basic one. Once the locomotive had been built in the factory, how did they get it over to where it was going to be operational? Or was it assembled at the place where it was going to operate?
No, that's an interesting one because moving tons of hardware around is not easy in that time. They used to ship it down to, used to move it by road, by a dray, a horse-drawn dray, down to the riverside, the Tyneside, and using ship's derricks, they would lift the loco in component form. That's to lift the boiler, lift the wheels, we lift the frame all separately. And then when they arrived at the destination, it's Liverpool or wherever, they would then place it and re-erect it on site, which meant that one of the senior foremen from the Newcastle works would need to accompany it. A bit like Edward Fletcher going down to the Canterbury and Whitstable. He then had to supervise the discharge of the loco at Whitstable Harbour, but it wasn't a harbour, for quay, with the ship drying out at low water, and then lift the locomotive using the ship's derricks from there to the quayside. So it was not easy. In the Rocket's case, such was the urgency of needing to get it to Liverpool in time for the Rainhill trials, that what they did was, in fact, abandon the idea of putting it on a ship, sailing it all the way around the coast of Scotland to Liverpool, because the ship that preceded it, the one with the locomotive for the Baltimore and Ohio Railroad that I mentioned, I undertook a research to try and recover the components of the loco. That must have frightened them, because if that had happened with rocket on board, that could have catapulted the effort for the Rainhill trials. And so what they did then was to move it across on the road using a horse-drawn dray, drew it from Newcastle across to Carlisle, and in Carlisle they then put it on the vessel to sail it down from Carlisle all the way through to the Mersey, and that's sped up the journey no end. And then they were able to discharge it at the Liverpool quay and assemble it ready for the trials.
Keeping me fit, this.
just a quick one. Do you know what it called the rocket? Because at that time there weren't any rockets, and there was no such thing as rocket propulsion. So where did the name come from?
Right. Well, there have been speculated. There is no document that I'm aware of that says rocket was called rocket because of. But in fact, the word rocket was understood because of the military use of rockets, which were known about, having been introduced by a chap called Congreve in the first decade of the 19th century, and they were spectacular, and they sparked, and they So when you saw a rocket running along the track at anything like speed, then the sparks that were ejected reminded people of Congreve's rocket. And so that is a possible explanation, but there is no hard and fast evidence that says that was the reason.
Michael, did they have many problems with material failures,
Yes,
such as fatigue,
enormous
fracture?
I'd rather stop too soon by saying September 1830, because there were, as a result of the innovation that had been that all happened during the course of 1830, they hadn't got time to prove the materials, and the work in the next 5, 6, 7 years was to improve the materials no end.
Right.
There were wheel failures, axle failures, motion failures, there were all sorts of failures. The alarming thing is that the failures took place in service with people on the trains. And this was very concerning for the directors, obviously. The Stephenson company were working flat out to try and introduce improved materials. And the first thing was an improvement in the quality of the iron.
Yeah.
But certainly for the wheels. So the wheels that was subsequently used from the mid 1830s onwards were what they call gas pipe wheels. In other words, they had wrought iron tubes, which they laid in the foundry, laid down in the mold foundry, and poured in the cast iron hubs and rims around them. That was the first thing. But they took quite a while to become failure free, if that's the term, before they then moved on to forging the wheels from scratch. The main contention, though, that went on for many years, a good decade or so, were the crank axles. There were significant failures of crank axles, and no matter how hard they tried to improve the quality of the material.
Yeah.
The iron was obtained as soon as possible from the Low Moor ironworks in Yorkshire, because the Low Moor iron was much higher quality than the Bedlington iron that they previously used. And it was only as a result of using the high quality with the bowling iron as well as the Low Moor iron that things started to improve. But it was a very difficult first few years.
Yeah. Thank you. Time for one more question.
Did the rocket finish off the idea of coupling rods between the
going
wheels?
back to the use of coke, when the requirement was put into the Liverpool and Manchester Act that the engines should consume their own smoke, what did they envisage? You know, what was the how did they know that was going to be possible?
Well, I mean, coke had been around for quite a long time, and it was known that burning coke is far less smoky than burning, coal from scratch. So I imagine that they had in mind the coke anyway, but the drafters of the bill that became the Act, that they would have been very cautious about how they worded it. So in case there were alternative improvements that could be made, then they phrased it in those terms.
One more question or comment on the Fred, do you want to ask your question, please?
Yeah, I got two questions really. One is that did the rocket finish off the idea of coupling rods between the wheels for many years? And secondly, those internal flues, especially the double flues, there was a real danger of them collapsing, wasn't there?
So the first question was on coupling rods, and the second one was about the collapsing, the risk of flues collapse, the double flues collapsing. Right. Okay. Yes, the risk of, excuse me, the risk of the flues collapsing on the Stockton and Darlington line was really quite serious. I mentioned about the second loco that was removed from service completely because it was badly damaged. What was happening is that as the locos were proceeding on the track, the safety valves, but because of the vibration, the safety valves would move up and down with losses of steam for every movement. And so what the crews used to do was to tie the safety valve lever down with rope to stop it doing that. Now that's okay if you're using the steam, but when you get to a point where especially on a single line, the track prevented you from the traffic prevented you from proceeding along the line, then you had to stop. And then did you untie the rope that was holding the safety valve down, or wait for your opportunity to move? And on a number of occasions, the crews were so tied up, especially when there were mixed traffic with horses in front of you, they were so tied up that they sometimes forgot to untie the safety valve lever. And it was on those occasions that the explosions took place. So there was the first one, on number 2, which just destroyed the loco. The second one on number 5, which was then the Diligence, but before it became number 4. That was the second one that failed. And the third one was number 1 itself, the Active, which, as I say, the driver was killed. Now, what was happening is that the quality of the iron was poor. That we do know, because my colleague Peter Northover joined us on 1 or 2 occasions up in Shildon and took samples from the boiler plate of the locomotive, which I say the boiler dated from 1827, and said that how poor the quality of the iron was. So that's the first problem that they had. But secondly, if you've got the flue riveted the plates of the flue riveted together and then in turn riveted to the boiler barrel, there are points of weakness that you have to accommodate. Well, if you tie the safety valve lever down, then you're asking for trouble. And the directors used to fine the drivers 10 shillings, which is a huge fine then, for every occasion that they were found to have tied it down while stationary. And so they were trying to minimize the occurrences, but sadly on some occasions they did not succeed.
I'm sorry to everyone. I'm aware there's 1 or 2 more questions online. I'm going to pass those over to Michael after the meeting and see if Michael will come back to you on email on them. We're very much running out of time now.
Well, thank you, Michael, for that wonderful talk, and thank you for answering all the questions. Very, very impressive indeed. Can I just make 1 point about Michael's work? He's written a number of books on this topic, and one I recently bought was the title Made in Britain, a wonderful read, and it covers the manufacture, the design, and the development of locos. So if you want a good read, that's worth buying. You can buy it on Amazon as well. Thank you, Michael. Anyway, thank you. Can we thank you?
To those online, sorry about the minor sound qualities at the beginning. We'll try to correct those on the recording. It was due to circumstances completely outside our control when we got to the bottom of it. Bye.
Thank everybody for attending, and thanks for the questions as well. We're very, very interested indeed. Thank you.